Good morning, everybody. Thank you, Fox. Thank you, Corey. All right. Based on your schedule, let me show you this schedule and how it is working. Thank you, Ronald. Um, Here. Okay. So I am trying to follow this spreadsheet, and every once in a while, I am a little off, which means, for example, today, I have already talked about 15.4, and we are going to skip 15.5. So today I will start chapter 16 and talk about 16.1 to, I don't know, possibly 16.3, so that during your spring break, you review those material and you get better at it because you are going to have test the Thursday after spring break. And I don't want to cover these materials, 16.2 and 3 both, um, on Tuesday and then give you a test on Thursday. So you better have some ideas that what 16.1 to 3 are. And during the spring break, please, I strongly recommend that you uh, read those through three sections and get good at it. Okay. Any comment, any question? So in chapter 15, eventually what we did was use of Taylor theorem. And theoretically, Taylor theorem, of course, helped us. And later, we used Taylor theorem to find the power series representation of a function. So that's all we did in chapter 15. Now, let me remind you that Taylor series, the way it works, this is the way Taylor series works. So we have a function which is analytic in a simply connected domain. So this domain right here doesn't have any hole in it, right? So the point alpha is not a bad point. And the function is analytic here, meaning that derivative exists everywhere in this domain, okay? Now, if that is the case, we can have a power series representation of the function with center being alpha, all right? Center being alpha means in powers of z minus alpha. We have a power series representation in powers of z minus alpha. What about these coefficients? What are these? Well, those coefficients are actually here, the nth derivative of the function evaluated at alpha divided by n factorial. But if we use the Cauchy's integral theorem for derivatives, this is exactly 1 over 2 pi I. f of s divided by s minus alpha to the n plus 1. You are integrating over ds. And what about this c? C is this any closed curve. Usually we choose the simplest one, which is a circle, all right? So it is any closed curve that contains alpha inside. So that is the coefficient. Well, we used this theory to find the important power series, right? For example, we found the Maclaurin series or power series of e to the z, which is this one. Here, alpha is 0. Of course, we can have alpha something else, but this is it. Here is for cosine z. And here is for sine z. And these three are valid for all z's because the function on the left, exponential functions, sine z and cosine z, those functions are entire functions. They have derivatives everywhere, all right? So we also had this geometric series, but this is valid only when absolute value of z is less than 1. Okay. One of the facts that we proved and we should keep in mind religiously is that when you find a power series of a function, no matter what method you use, that power series is always unique. All right? You cannot have two different power series for a function. No, no way. So this fact will enable us that we, instead of directly using the Taylor series, Taylor function, use some sort of shortcuts, okay? So that was a quick review of chapter 15 and what we did. And those shortcuts, I gave you enough examples, hopefully that you understand how to use those shortcuts and be good at it. All right. Now, so let's look at this again. In Taylor series, the function is defined in here, simply connected domain, and there is no singularity. There is no bad point here. The function is beautiful function, has derivative everywhere. And the domain is simply connected. Simply connected means it doesn't have any hole. And you know, we created those holes when we have a bad point. Okay. So now the question is, what if this alpha is a bad point, is a singularity? Well, in that case, instead of Taylor series, we have another type of series which is called Laurent series. Okay, today I want to talk about Laurent series. Here is the Laurent series. So the function is analytic in this washer head, which means alpha is a bad point. Alpha was a bad point, and we isolated alpha with that little disk. But the function itself in this is very well behaved in this washer, all right? Can we write a power series for this function with center being alpha? And that is the topic of Laurent series. Yes, we can. But since alpha is a singularity, in this power series, we are going to have negative powers of z minus alpha. Negative powers. Okay. Well, just look at this symbol. N goes from negative infinity to infinity. But in Taylor series, N goes from 0 to infinity. But as soon as alpha is a bad point or is a singularity, we are going to have negative powers. How about these ANs? Well, the same formula for AN is going to work. 1 over 2 pi I, integrating over any closed curve that contains alpha. Usually we choose just this one circle, right? Just this circle of radius r. Okay. The rest is quite similar to what we had in Taylor series. The difference is in Taylor series, n was 0, 1, 2, but here n can be negative. N can be -1, -2, and so forth. All right. Well, I have good news for you, though. When you write Taylor series, Laurent series of a function, that series also unique. Well, in finding Laurent series, and from now at this point on, we are going to find Laurent series. In finding Laurent series, because it is unique, we can use shortcuts. Okay, we can use shortcuts. Your first example, here is the first example. I want to use, oh, look at this function. There are 2 bad points here. In denominator, zeros of denominator are bad points or singularities. 0 is 1, and z equal 1 is another one. So here is the bad point. Here is one of them, 0. Here is 1. Okay. But we want to write the Laurent series that is valid whenever modulus of z is between 0 and 1, which means you're choosing the point inside this disk, every point except 0. So the modulus of this point will be less than 1. It is inside the disk, and it is bigger than 0, which this part just indicate that we are not choosing 0. All right. There is also another hint here. Whenever you want to do such a thing, it basically tells you, go ahead and find the series in powers of z. In powers of z. All right. Here is what we do. This is the function. If I want to write this in powers of z, I will not mess up with this one because it's already in powers of z. So I only need to look at this function and express the rest of it in powers of z. Okay, here is, let me tell you why. If I want in powers of z, then the function looks like this. 1 over z times one over minus c. So I have no problem here. It's already in powers of z. So we need to take care of this part. But we know geometric series. We know that this is true whenever modulus of z is less than 1. All right? This is always true. Now, all we need is multiply this part by 1 over z. And here it goes. You multiply this by 1 over z. This is what you get. Here you get 1 over z. Here you get 1. Here you get z, and so forth. This is the Laurent series of that function that is valid in that washer, excluding 0. So the right-hand side converges all the time to this function right here. Okay? Oh, that's one way to do it. There is another way, of course. We can use partial fraction. We can say, oh, look, this function right here, if we do partial fraction, this is what we get. So it is 1 over z plus this part. And now, since modulus of z is less than 1, we can replace this one by that geometric series right here. Okay? So this is the function. This is the second method that I thought you might also apply. But you only need to learn one of those techniques. If you're good at partial fractions, why not do it that way? Okay, any question about this particular example? All right, I don't see any question. So I'm going to give you more examples, of course. That's how we apply this Laurent series, remember? And later, we are going to have observation about this Laurent series theorem and get some very good observations and facts out. So here's your second examples. Consider this function. Oh, again, this function has 2 zeros in denominator. One is 0 right here. The other one is what? Well, we wrote in previous example, we wrote the Laurent series that was valid in this disk, okay? But now I want to write the Laurent series of this function, which is valid outside the disk, which is valid right here, outside, when modulus of z is bigger than 1, okay? When modulus of z is bigger than 1. Well, again, as soon as you see such a thing, you're talking about modulus of z. That pretty much means you want to find the Laurent series in powers of z, right? In powers of z. And again, if I want to write the Laurent series in powers of z, I will not mess up with z squared because it's already in powers of z. So I will write the function in this format that, look, f of z is 1 over z squared times this. So this part is fine. It's in powers of z. We need to take care of this part. When modulus of z is bigger than 1. When modulus of z is bigger than 1, you take reciprocal here, modulus of 1 over z will be less than 1. All right. Okay. So here is this part of that function, 1 over z minus 1. If I factor z, denominator, I will not have any problem with this. It's in powers of z. Denominator becomes 1 minus 1 over z. Now, to this part, I can apply geometric series because modulus of this guy is less than 1. So 1 over z, call this one w, and here is the geometric series representation, all right? So this is just 1 over z minus 1, power series representation, then modulus of z is bigger than 1. Now you multiply by this factor, and you get, all right? So you multiply this by 1 over z squared, you get this. Now this is the Laurent series of this function, which is valid whenever modulus of z is bigger than 1. Okay, so here is, I multiplied out. So as you see, in this case, we have all negative powers of z. We don't even have a constant. We don't even have z. Oh, here, we don't even have 1 over z. So in writing the Laurent series, it is very well acceptable and happens a lot of time that you only get negative powers. Or you might get combination. You might get some negative powers and some positive powers, like previous example, Oh, look at this previous example. I have a negative power as well as all here, positive powers of z. Okay, but this is valid in modulus of z less than 1. Okay. So if you write the Laurent series of a function, and it just happens that you only get all negative powers of z, that's perfectly fine. That's perfectly fine. Any question about this second example? Okay, I don't see any question. Let's see. I'm going to, well, here is another example. Now, for this example, here is the function. Again, looks like the function in example 1. But this time, I want to write the Laurent series that is valid in here. When you look at this, anytime you look at this, right away, you realize that, oh, they're asking the Laurent series in powers of z minus 2. In powers of z minus 2. Okay. So here is 2. 2 is not a bad point here, of course not. But the bad points or the singularities is here 0 and 1. And what we are after, we want to write the Laurent series, which is good in this washer. Z minus 2 means a circle centered at 2. All right. The modulus of z minus 2 equal to means this outer circle. The radius is 2. Modulus of z minus 2 equal 1 means center is 2, radius is 1, which is this one. So we want for all z's such that z minus 2 is between these two circles. All right, z is between these two. Z is in this washer, okay? All right. Be careful. We want in powers of z minus 2. Well, it would be nice if we can do partial fraction. Okay, here is the partial fraction. Those of you who have forgotten partial fraction, of course, you can go ahead and review how to do partial fraction. So this is the function. It has two parts, this plus this. Oh, I'm calling this one f1, this one f2. Each one of these, f1 and f2, we want to write in powers of z minus 2. And of course, we will use geometric series. But in geometric series, okay, here is f1, which is just negative 1 over z. We want in powers of z minus 2. Why not? Let's make z minus 2 appear somewhere. So we add 2 and subtract 2. Here is z minus 2. But if I want to use that geometric series, the geometric series looks like this. 1 minus W. And 1 minus W, whenever modulus of W is less than 1, is going to be 1 plus W, W squared, and so forth. Only when modulus of W is less than 1. Okay? Remember this one. So, although I added and subtracted this 2, but I want to make this format appear. 1 minus something. Oh, well, just factor 2, you will get 1. And whenever, call this one W. When modulus of this is less than 1, we can use this. All right. Well, here, since we have plus, remember when we have plus, you will do the plus part, 1 plus. Just replace W by negative W. It will be 1 minus W plus W. It alternates. And again, modulus of W has to be less than 1. So I do have this format right here. I will apply it. So it's going to be this. Okay, so F1 is written in powers of z minus 2. And in this case, we want modulus of this be less than 1, which means modulus of z minus 2 less than 2. And that's good. That's good, because it is right here. Modulus of z minus 2 is less than 2. Okay, that's good. So this is valid for every point inside that bigger disk, including in that washer. Now, how about the second part of the function, f2, which is this one? Here comes f2. Again, I want in powers of z minus 2. I better make z minus 2 appear, right? So I add 1 and subtract 1. That's what you get. All right, if we factor z minus 2, this is what you get. And if modulus of this is less than 1, which means modulus of z minus 2 bigger than 1, and that's exactly what we need. This is what happens using that, again, geometric series. So here's how we are using the shortcuts, okay? Using geometric series basically means we are using the shortcut. Good. So here is the second part of the function. Now putting both together, here comes the power series. All the negative powers right here, all the positive powers of z minus 2 here. So we have combination. So, all right, all the negative powers of z minus 2 and all the positive powers of z minus 2. This example was extremely crucial, nice, and I think this example can be a very good guide for you to do the problems concerning this Laurent series. Okay. Do I have more examples? Oh, yeah. This is just for you to practice on it, all right? So here is another one. I think you should practice this one. We want to write Laurent series of this function, valid in here. Oh, look, this is giving your hint that you want in powers of z minus 1. So when we want in powers of z minus 1, we don't mess up with this. It is already in powers of z minus 1. So you write the function in this fashion. And just work with this one. And write the series of this function in powers of z minus 1, which is valid in here. Okay, it's valid in here. So I will let you do this by yourself. It's a good practice. Okay. Any comment? Any question? I don't know if you're awake or not. Are you? Yeah, Ronald Diaz. Thank you. Bill Dodson is also listening. That's fine. No question. Interesting enough, for the first test, 33 students took the test. 33. And now I have only 13 students in my class listening. Well, that is fine. I don't want them. I don't force them to be present in the class. If they have the talent and they have the ability to learn the material by reading it through the book or text or whatever, that's perfectly fine with me, right? That's perfectly fine with me. Okay. Now, I am trying to remind you that what we did so far. So if the function is analytic here, then not only if prime exists, but all derivative exists. We already saw that in earlier chapter. And the function can be written in a power series in the powers of z minus alpha. Which part? This part was Taylor series. AN, what is AN? AN is right here. Okay, just again, as a reminder. But what if that alpha is a singularity? So that part, the first 4 lines are Taylor's theorem. When alpha is singularity, then f of z is not analytic at alpha, and still we want to write the power series of the function in powers of z minus alpha. That will be the Laurent series. Okay, that will be the Laurent series. Now, when alpha is a bad point, from this point on, we will call it singularity. There are several types of those singularities. Well, here is a function. There are only two bad points, zeros of denominator. Okay, zeros of denominator. We call this type of bad points isolated singularities. Isolated singularities, all right? But there is another type of singularities, which we call non-isolated singularities. Non-isolated singularity example is like logarithm. Oh, remember, logarithm doesn't have derivative on the left side of x-axis, and zero, of course. So this function doesn't have derivative only at that point and this point. We can isolate this. But when it comes to logarithm, here is -3. Doesn't have derivative here. And you cannot isolate this because any disk you consider centered at. So there are infinitely many other points that the function doesn't have derivative here, all right? So this is called non-isolated singularity. Non-isolated singularity. All right. We would like to classify. In this course, we will not really dealing with non-singularity, non-isolated singularities, but mostly we will be dealing with isolated singularities. We are going to classify these isolated singularities, all right? And remember, these isolated singularities, alpha, f prime does not exist at alpha itself, but exists in this neighborhood. Derivative exists in this neighborhood, except at the point. Like this one, this function is not even defined at 3i. But in a disk centered at 3i, let's say radius 2, the function is perfectly nice function at other points, not 3i, other points. Okay, so what is the definition of isolated singularity? Here is the definition. It's a point where derivative does not exist at that point, but there is a disk centered at that point. Derivative exists at all other points of that disk, which means right here, okay? All right, so these type of points we want to classify. How do we classify them? Well, by writing the Laurent series. Laurent series centered at this point. If this is a bad point, clearly we are going to have negative powers of Z minus alpha, right? Okay, good. Let's classify them. You write the Laurent series with center being Z naught or alpha, right? Doesn't matter. Oh. So we know that there is a Laurent series, and AN is this one. One beautiful observation here is this. When n is -1, a sub -1 will be just 1 over 2 pi I integral of f of s ds. And usually in integration theory, we are after that. We want to see what is the integral of f of s ds or f of z dz. Okay? So if you replace n by -1, you will get this. So integral of f of z dz is 2 pi I times this. What is this? This is the coefficient in writing the Laurent series. A -1 is the coefficient of, put -1 here, coefficient of 1 over z minus 1, z0. All right? That is called residue of f of z at that point. So, and that residue will, later I will come and talk about this residue, finding residues, and there is a beautiful theorem called the residue theorem that will help us to, in integration, to integrate a function. So, how do we find this? In Laurent series. This is it, the coefficient, the number that is multiplied by 1 over z minus z naught. If we write the Laurent series, this is the most important number we are after. The most important number, because it gives us the integral of f of c dz. It is 2 pi I times this number. All right? Okay, good. Well, we have some sort of naming or terminology here. When you write the Laurent series, this part, constant and positive powers of z minus z naught, this part is called analytic part. Of course, it is analytic, right? Okay. But the other portion that contains the negative powers of z minus z naught, this part is called principal part of the function. Okay. Now, based on that principal part, we are going to classify this singularity z naught based on this principal part. Okay, good. Remember, I said I want to classify those singularities. All right. So we will concentrate on the principal part, the part that has all the negative exponents of z minus z naught. Well, that is the principal part. This is the analytic part. Okay. For isolated singularities that we want to classify, one category of isolated singularity is called removable singularities. Removable singularities. How do we recognize these type of singularities? Well, always we write the Laurent series. And after writing the Laurent series, like this one, you see, the function sine z over z. Oh, z is a bad point. Z equals 0 is in denominator, right? Bad point. But if you write the Laurent series centered at 0, here is 1 over z times sine z. This is sine z. And multiply this out. Oh, well, the negative exponent of z vanished. All right? So this function, after writing its Laurent series, doesn't have any negative exponent of z. This type of thing is called removable singularities. Okay. The second category of singularities is what we call pole of order n. Poles of order n, when you look at the principal part, which contains the negative exponent, terminates here. So beyond this one, we don't have any other. So the largest exponent of denominator is n. If this is the case, we call z naught a pole of order n. It is isolated singularity, all right? It's isolated singularity is pole of order n. And if n is 1, which means up to here, only we have this one, not this, then we say it's the simple pole, okay? So if it is pole of order n, we factor this. Everything that we get from, if we factor this, will be a constant here, and all of them will be sort of positive exponents of z minus z naught, which is analytic. So we can write it in this fashion. So how do we recognize that this point is a pole of order n? Well, like this. After factorization, you get this one. But phi of z is analytic at z naught and is not 0 at z naught, all right? It's not 0 because this is not going to be 0. Okay, so this is a Very interesting observation. So a function has a pole of order n. A function has a pole of order n if and only if. Sorry, just a minute, please. Hello. My apology for this interruption. So, when it comes to singularities, so far I introduced two categories. One is removable singularities. How do we recognize it is removable? After writing its Laurent series, all the negative exponents of z will vanish. You will be left with all positive exponents of z. If such a thing happens, we call that bad point z equals 0, a removable singularity. But if you write the Laurent series and you get such a thing, and this number is not 0, then we call it a pole of order n. Another way of recognizing that it is a pole of order n, the function can be written this way, where numerator is analytic and is not 0 at this point. But in denominator, you have z minus z to the n, okay? This is, in this fashion, of course, the principal part, remember, principal part is all the negative exponent. We have finite number of terms in here, right? We have only n of them. In category number 3, when you write the Laurent series, the number of negative exponents will be infinitely many. All right. If you have infinitely many here, then that one is called essential singularity. Essential singularity. So here's an example of essential singularity. I want to write the z equals 0 is a bad point right here, okay? Actually, it is the only bad point. For this function, z equals 0 is the only bad point. But I know that e to the z or e to the w is a beautiful function, is an entire function. This is valid everywhere for all w's. So I replace w by 1 over z. And I will get this. And even if you multiply by z cubed, see, you are going to have infinitely many negative powers of z. This is the type that we will call essential singularity. Essential singularity. So z equals 0 is essential singularity for this function. Okay? Here is the, after multiplying by z cubed, here is the analytic part, constant together with positive exponents of z. And here is the principal part. Doesn't terminate. It goes forever. The negative exponents of z will go forever. Okay? This type of singularity are called essential singularity. Here is an example. Z equals 0 is a bad point. Z equals 0 is the only bad point actually here, right? So the question is, what type of singularity is this? What type of singularity is this? And can we use it one of those classifications? Is it removable? Is it a pole? And if it is a pole, what is its order? Or maybe it is a essential singularity. We can answer these questions by writing the Laurent series of the function. Well, in this case, it's got to be in the powers of z. So here is cosine z. Divide by z cubed. Here's what you get. Here's all positive powers of z. Here, all the negative powers of z. So it is a pole of order 3. Pole of order 3, all right? Okay. So z equals 0 is a pole of order 3. Any question? Any comment? Could you please elaborate on that question, Brandon? Anyways, yeah, your question is not okay. Like, what section is the negative points and which aren't? Well, okay. So this section, after writing f of z, it's Laurent series. The positive exponent of z and the constant is what we call the analytic part. The terms that are in denominator, okay, those are the ones that we say negative exponent. See, in this case, the principal part, I'm saying that is this. After multiplying this by 1 over z cubed. These are negative powers of z. Why? Because we can write this as z to the negative 3 minus 1/2 z to the negative 1. This is what I meant by negative exponents of z. Negative exponents of z, by writing it, I mean, in the denominator, there will be positive, of course, right? But you can write it this way. These are negative. So if you write the Laurent series and you don't have any terms like this, then you have a removable singularities. If you have a finite number, or in this case, you see, we have just two terms. This one, the largest in denominator, is what we call whole of order 3. Whole of order 3, okay? But sometimes this will continue forever, if that is it. Now, here we have just two of them, right? You can have 10 or 100, that's okay. But if you go infinitely many of these terms, that is when you call essential singularity. Essential singularity, all right? Okay. Okay, now that I explained the negative powers, Brandon, let's look at this one to make sure that you see the negative powers. See, after multiplying this example, here are the positive powers and the constant. This part is good. This part is good. We call it analytic power section or part. But look at this part. Here I have 1 4 factorial z negative 1. Here I have 1 5 factorial z negative 2. The next one, 1 over 6 factorial z negative 3. All right. You see, this part goes forever. So this is the part which we call principal part. And how many terms do I have in principal part in this case? Infinitely many. That is when we call it an essential singularity. Okay? All right. What else? Let me see if I have another example for you. No, I don't. So I'll stop right here. That pretty much covers sections 16.1 and 16.2. Please look at those. As you see, the material is not that challenging. It is just a matter of getting used to those terminologies. Please go ahead and read those two sections and try to do the problems. And if you have any question about those problems, you can ask me on Thursday. And on Thursday, I will talk about section 16.3. All right? Any comment, any question? Wonderful. I don't see any question then. I will see you on Thursday. Have a good day, everybody. Bye-bye now.